All right, let me go ahead and get started. I first wanted to say a note about the quizzes, the online quizzes. There's always this dilemma for the quizzes I offer in this and similar classes. I want to just give a few questions which will be the material in its entirety that you need to understand for this course. What that generally amounts to is 5 or so questions. And what happens is, 1, it's the first time you're seeing this material, and 2, it's only 5 questions. So if you make a silly mistake on 1, your grade goes down to a B minus. You make a silly mistake on 2, your grade goes down to an F. So I've thought about how I approach that. And one thing I want to do is just assure you that it's the hardest material you're going to see in this class. And if you learn this stuff on the quizzes, you will be prepared for the final exam. And 2, often I'll make a deal with the students where you get to reset one course or one quiz of your choosing if you do kind of poorly on one of them. But what I actually want to do for this class, I think I sent you an email about resetting the first 2 classes. And I haven't looked at the quizzes for this week yet. Actually, I looked at yours, but I haven't looked at anyone else's because today was kind of crazy. But I imagine the trend is going to continue because the material we covered last week is a lot. It's tough. So, So the first time you encounter that probability and just getting your head wrapped around those Venn diagrams and to have to reproduce that on one question, which is pretty much the chunk of your grade, is tough. So what I think I'll do is just reset all 3 of the first quizzes. Reset the first one, the second one, and the third one. So what that means for you all is you should look at the quizzes. Do you know how to look at the quizzes and see what the answers were and what you got right and wrong? Okay, so good question. Those of you watching online, I will go over that for everyone's benefit. What you do is you click on the quiz, like you click class 1 quiz or class 2 quiz. Hey Shiba. Then you will click on the score that you got. It'll be like 3 out of 5 or whatever the score is. And that should pull up all the questions and with the answers for the correct feedback. Shiva, have you looked at, have you done that before? Have you looked at the quizzes and looked at the answers?
I was trying to find it, I couldn't find it.
Okay, so I'll just repeat that again. So you'll click on, or you first do go to My Grades, and then you'll click on the quiz, and then you'll click on the score, the number that you got, and that should pull up everything.
Okay.
And you should look over the questions and look over the right answers and make sure you're able to do that quickly for a number of reasons. 1, because that's the material you'll need to know for the final to do well in this class, and 2, as I sent an email about and I just expanded it a little bit, I want to reset the first 3 quizzes and just have you do those exact same 3 quizzes over again, because this first 3 weeks, actually week 1 and week 3 are awfully tough. First time linear programming, algebra, haven't done it for 10 years, have to dust that off and do it in a optimization type of setting is tough. And then the last week, I don't know if you've taken the week 3 quiz, but I haven't looked at it. You didn't do so well? Okay.
I was stressed.
That one,
I think at the time was...
that one is tough too.
Yes.
So I'm going to give you a second chance on that.
Great.
And then the finance one, I don't think there's anything too difficult about the finance stuff in class 2, but there's always, if you make, just like I mentioned, if there's only 5 questions, you make 1 silly mistake, and then all of a sudden B minus, make 2 silly mistakes, all of a sudden F. So there's no reason why you shouldn't get just all the points on that, because I want you to, over the next couple of days, look at those answers, make sure you're able to do them, and then I'll reset it. What do you think? Should I reset it Saturday?
Yeah,
Saturday? Okay, I'll reset it during the day on Saturday. So you have between now and Saturday to look at all the answers and work them through, et cetera, and then after Saturday, you can just retake the exact same quizzes. All right? So with that, one thing I wanted to do while we're still on it is I actually just wanted to go over quiz 3. The quiz that you just took for this class and the review of last week. I just want to go over those questions and make sure we've got them all. All right. So first we had a couple questions on union and intersection. So let me jot those down. You are given two sets of numbers, and you're to tell me, is this union or is this intersection? And remember, union is the one with the U, and intersection is the one upwards down U. And what does union mean? Or. Okay, this means or. So, part A or part B. If it's included in either or, it is in the union. And intersection is and. All right? It must include both A and B to be included in the intersection. All right, so let's see what we got here. We got two sets of numbers. We got 2, 1, 7, 13. 2, 1, 7, 13. And union or intersection. 1, 5, 9, and 13. 1, 5, 9, 13. And the answer to the question, union or intersection, is going to equal 1 and 13. Boom. Your job is to put either union or intersection in between. And the answer is intersection. I like it. Intersection, meaning what is in this set and this set. And the numbers I see that is on both sets are 1 and 13 here, 1 and 13. If it said union, then we would include all those numbers. Make sense, Shiva? Intersection. 2 is in this set, but it is not in this set. And intersection needs to be and. All right, what is in set 1 and set 2? So the correct answer is intersection. All right, you keep looking at that. I will write out the next question. Okay. Any questions on this, first of all? Does it make sense? Making sense? All right. So the next question, we have two sets of numbers. One includes the number 1 and 7. The other includes the number 1. And we're going to put either union or intersection. And when we do that, we're going to get the answer 1 and 7. Your task is to tell me which of these mathematical symbols do I put in between them? Do I put union or do I put intersection? Shiva? Union. Yes. Yes. Union is correct. All right. If I were to put intersection, like what is, so 1, 7, intersection, 1, right? That would equal something different. That would say what is in both of these, and the answer to that would be 1, right? But union is what's in this one, and in this one. What is in all of them? A little bit tricky because this includes both 1 and 7, but the correct answer is union. Does that make sense? Yes. Fantastic. All right. Let's look at question number 3. Assume that a single spin of the roulette wheel is made. Please find the probability that the marble will land on an even or black slot. So you can look at the roulette wheel in your textbook. What is the process we're going to go through to answer this?
Was that the tree diagram?
No, this was not a tree diagram.
Okay.
This is a single set spin of the roulette. All right. All right, so for this, we need the number of events divided by the number in the set. Look familiar? Alright, so our probability of a certain event is going to equal the number of events divided by the number in that set. So we need both of those pieces of information. So let's take a look. A single spin of the roulette wheel. Let's see, how many total slots are there on a roulette wheel? 30? 38, yes. So if you had your textbook open, you could just count, and you would see 38 total slots in this sample space. So you need to go through and count how many are even or black. So you'll just
17, I think it was 17 or 18.
yeah. Well, you just I think the way to do it is to just go around and count. That's what I did when I constructed this problem.
Yeah, that's what
Yeah, we can just let Nikki count for us. 18? Really?
27.
27? I like 27 more than I like 18, but
All black. There's got to be 18 black.
so even and black. I like 26 for this. If I'm wrong about that, then please let me know. But I think because it gets confusing, even black, I don't know if there's a clear system working out the mathematically. I just look and count.
There's got to be half of them is even, so that's 9 on the red side, and black, there's 18 black.
Altogether it's 26.
What?
Like 18 black and 18 black.
Just count. Just go through. Like, is this black? Is this even 1? Is this black? Is this even 2? 1, 2, 2, 2, 2. I don't know how many even versus black even.
26, okay.
You like 26?
Mhm.
Yes. All right. I've got one supporter in my cult of 26. All right. So, yeah, there's no need to spend too much time on it now. Just you can, privacy and comfort of your own home, you can count how many there are there. But that's how you do it. You count how many different ways you could win the bet. You get 26 over 38, which simplifies to 13 over 19, right? You could crunch that into a fraction, and that would be acceptable as well. Make sense? All right. The next 2 questions involve a Venn diagram. So let's construct that Venn diagram. And remember, the trick to the Venn diagram is do all the work ahead of time. Sort of on our front load the work, so to speak. And then we can just pick off the various answers. So let's draw a nifty Venn diagram. Perfect. All right, now. All right, so we've got circle A, and we've got circle B. I think that's what they were called on the quiz. Yes. And we're given certain probabilities. We are given. Let's take a look here.
Quiz 3.
What's that?
Is this from quiz 3?
Yes.
From what?
This is the review. Yes.
Oh yeah, quiz 3. Yeah, it's quiz 3, and it is question 4 and 5, I believe, give us the same, have the same stuff. Okay, so we know the probability of A is 37%, probability of B 41, probability of A union B is 65. So probability A equals 37.37. Probability of B equals 0.41. And probability of A union B is 0.65. Okay, so what do we know and what can we calculate based on that information? We know the probability of A union B, which is all this. A union B, so A or B, so all this, all this, all this, all together is 65% of the whole. We also know that the probability of A by itself is 37%. So given everything together is 65, and the probability of all this A is 37%. So we know that 65 minus 37 is going to be just this part of B, right? So what do we get when we crunch that out? 65 minus 37. .28? I like it. All right, 0.28. Now we can do a similar calculation over here. We know that B by itself is 41%, and we know that A and B all together is 65%. So, knowing that A and B together is 65, all of B is 28, what is this part of A? Just this part of A, not including this part of A. We know altogether 65, and we know that B is 41, which leaves a remainder of this part. 0.13. 14? 0.4? 13? What's 65 minus 41, right? It's the difference. 0.24? Does that make sense, Shiva? 0.24? Okay, so we know that this whole thing together, A, the middle part, and B, is 65.
Right.
We also know that all of B is 41. So we take 65 minus 41 is going to give us this part of A. Not including the middle part, not including the shared part, this part of A. And that's going to come out to 0.24. Okay, so we're rocking and rolling here. Let's figure out the part in the middle. Okay, the intersection. The part that contains both A and B. This sucker right here. Well, there are three components of this mix. There's A, just A, there's A and B, and there's just B. And we know that all that added up together is what? Yeah. Well, yeah, oh, maybe this is 0.13?
Yeah.
Okay, that may be true. But the question was, this part plus this part plus this part all adds up to what? 0.65, exactly. Exactly. And we already have 2 out of the 3 components that make up that 0.65. So what we do is we take 0.65, we subtract off the 0.24, subtract off the 0.28. What remains is that little section there. 0.13. All right, everyone agree? Fantastic. Now, all we need at this point is we need to know the outside, which is, we know this whole thing is everything in this universe. So what's outside the circle?
0.35.
0.35. Okay, because we know all this adds up to 0.65, so everything outside must add up to 100, or 1. 0.35. So we're rolling here. Now we're ready to answer these questions, which should be pretty simple. The first one says, please find A intersection B. All right, so A intersection B, or we could say the probability of A intersection B, all right, is this space in between, both A and B. A intersection B, 0.13. Right? Boom, we got that answered correctly. Question 4 asks us, probability of A given B. Probability of A given B equals. Now, how do we do this one? We can use the formula, which is, I think, the way we'll start. Once we use the formula and get it right, then we'll just back up and think about the intuition. The formula is the probability of A and B divided by the probability of B, right? Yep, divided by the thing that's already happened. So, we can crunch that out. The probability of A and B is 0.13, and the probability of B is 0.28. 0.26? 46? I believe A conditional A. So, right, 0.13 divided by, oh no, 0.13 divided by 0.41. I misled you there. So it's not just this part here. This 0.28 is just this section of B. We want the whole of A. So that equals 0.13 divided by 0.41 equals 0.32. So that is the answer. And you may recall that the example that resonates the best with me is, suppose you were working for the Air Force and you were doing target practice on dropping some sort of bombs, and you were to gather some intel that said, hey, guess what? We know the bomb landed somewhere in B. We don't know where, but somewhere in B. So with that information, what is the probability that it landed in A? All right, well, we know that 0.13 represents 32% of the entirety of B. Does that make sense?
But it doesn't make sense in terms of where it landed, though.
Well,
are you saying it landed in A and B?
Yeah, the chances of it landing, so the probability of A, given that it landed, the probability that this bomb landed in A, given that you know it landed in B.
So you're saying there's a 30% chance that it landed there.
There's a 32% chance that it landed in A, once we know that it landed in B. So, well, I guess just look at it, like, what's the probability of it landing in A by itself? Well, we won't look at it that way. So, what percentage, this A and B, what percentage is this little piece of the entire B circle? Let's look at it that way. So this little piece here, all right, how big is this compared to the whole B circle? So the whole B circle has a, has a area of 1. And what percentage is this little section of?
0.34.
Where are you getting 0.34?
Well, I thought we said the AB was 32%.
Well, okay, so this whole B thing altogether represents an area of 0.41. So out of this whole Venn diagram, 41% of it is encompassed by B. And we break this apart. 28% is just B, and 13% is this section that contains both A and B. But the whole thing together...
But it's got to be 62%, is that what you're saying?
The whole thing together is 41%. Let me draw it this way. This whole thing. This whole. The whole thing together is 41%. Guess that's, draw it this way. I drew it this way. Alright, this whole part is 41% of the whole universe. That's the starting point. So this B part, 41% of the whole universe. If I were to ask you the A part, like what percentage of the whole universe is that? Nikki? Yeah? 0.37. Am I saying her name right, by the way? Do you go by Nicole, Nikki?
Yeah, actually my first name is Nikita, but
Nikita.
you can call me Nikki.
Nikki. Do you prefer Nikita?
Yeah, Nikki is my bad name, so you can call me Nikita or Nikki.
Nikita or Nikki. Okay. Alright, sorry, Nikita. Okay. So, we need to be comfortable, Dr. Williams, with this B circle being 41% of the whole universe. So this whole, inside this box is 1, or 100. Inside just B is 41%. Next question is this little section here. Alright, this A and B contains both. What percentage of the whole universe is that? The whole 1.
Percentage of the whole universe? Or
Yeah, this whole universe is everything within the box. That's what I mean by universe. What percentage of the box is this section here? It's 13%, right? We calculated it. A and B is 13%. Right?
Yeah.
Yeah. So, you remember how we calculated that, right?
Yeah.
So, if we're comfortable with the fact that A and B is 13% of this universe, and we're comfortable with the fact that the whole circle of B is 41% of this universe, the question, how big a percentage is this part of B? Let's B. What if we call this just A? This is A and B. A and B. So A and B is 13%. B by itself is 41%. So if we were to look at this in terms of the whole sample space of B, we could call it 41% is all the possible places this bomb could have landed. Encompasses an area of 41. 41
Isn't
40.
A and B approximately 46% of B?
Is A and B?
A and B, the little,
Okay, yeah.
that's 46% of B.
Oh, okay, okay. So 46% of B. So you're saying
Yeah.
this little section encompasses 46%
Yeah.
of B. Okay, so you're on the right track. That's exactly the question we want to answer. Question is, how do we get there? How do you get 46%?
Well, just add and divide, right? I mean, just
So you got 46% somehow.
Yeah.
Let's stick with that. All right, you said 46%. How do we get that figure? Just look at
well, you just look at 28. You divide 13 by 28. 0.13 by 0.28.
Oh, okay, good. So 13 divided by 28. All right, what do we get when we divide 0.13 by 28? You check that?
0.464.
All right, equals 0.46. Okay, so we want to do some calculation kind of like that. And you're right on the top number, that this A and B together is 13% of the whole thing, but we need to make one adjustment with this bottom number. This 28%, this is just the part that's only B. This is this part,
Yeah, that's true.
the whole thing together, all of B is 41%. So, well, we take 0.3 divided by what we now know is the correct 41%, and we get 32%. So, probability of A conditional B equals 32%. Make sense? So, if we were on some sort of Air Force bombing drill, and I were to tell you, I know the bomb landed somewhere in quadrant B. I know it landed somewhere in quadrant B. I were to ask you, what are the chances that it landed in A? Which would be this section here. What's the answer? Dr. Williams? So, given that it landed in somewhere in B, what's the probability that it landed in A? So this is the probability of A given B. So knowing that it landed in B, we look at B as the whole universe. So what part of the whole universe? 41%. And we know that this sliver, where it could have been A given B, is 13% of the whole universe. Divide that and we get 32%. Make sense? Let me erase this bottom part and we can make sure that that's clear as necessary. Continuing questions on that?
Well, I just don't understand the question. Are you asking whether it landed in A or landed in B? I mean, it's unclear.
Yeah, so what's the probability of A given that it landed in B? So we know it landed in B. So now the question is, what's the probability that it also landed in A?
Well, we know it landed in B. It has no probability of landing in A.
Oh, okay, all right. So we know it landed in B. You're telling me there's no probability it landed in A? Let's stay on that. Yeah, we know it landed in B. Could it have, so we landed somewhere in B, so could it have landed in there?
That's AB, that's not A. That's AB.
Okay, so we know it landed in B. You just said there's no probability that it landed in A.
Right.
Okay, so we know it landed in B. Is there a way it could have landed in B and A?
In AB.
Yeah, it could have landed in, that's landing in A.
Well, that's not A, that's AB.
That landed in A. That's A, right, Nikita? This is A. It's A. It landed in A. It meets this probability formula. Right? You go back to your supervisor and say it landed in A. Landed in A. That's the only way it could land in A, because we already knew it landed somewhere in the whole B. Now, if these were, suppose, about A, B. Okay. Probability of A given B equals. Okay. This is now a different universe. Question to you, find the probability of A given B. The three of you think that through. Decide what you think your answer is. I'm answering this question. Probability of A given B. Well, you don't have any numbers at this point. I haven't given you any numbers, all right? For this, what's the answer? 0? Dr. Williams, what do you think?
put
Yes.
A to B. 1.
100%? Okay, so given that it's landed in A, alright, so this bomb dropped, and you dropped the bomb, bomb landing, somewhere in B. We know that for sure. Right, Shiva? We have good intel. We know this for sure. Landed somewhere in B. What are the chances that it landed in A? What are the chances that it landed somewhere in this circle? We know for sure that it landed somewhere in this circle. What are the chances that it landed somewhere in this circle? Nikita? 0. 0. 0. Yes. There's 0 chance that it landed in A. So the probability of A given B equals what, Shiva? What do we put in? What do we fill in for this? $57? 100?
Oh,
0?
right.
What's the answer here?
It has to be 100.
100? What do you like, Nikita? I like 0. 0. 0. Alright, so the probability of A given B is 0. You're comfortable with that? So let's go back to this question in this universe. Alright, the probability of A given B equals. So we have our little spies on the ground. Let me use blue here. Alright, blue is going to be the bomb. Blue is going to be the bomb. We have our little spies on the ground that told us it landed somewhere in quadrant B. Maybe it landed here. Maybe it landed here. Maybe it landed here. Maybe it landed here. We don't know where in B it landed, but we know it landed somewhere in B. So let me erase those so we don't get confused. So the question we have to ask is, how big is this little section compared to the entire B? We know it landed quadrant B. Now, the only possibility of it also landing in quadrant A is what, Dr. Wells?
In AB.
Yes. Yes. So the question we have to ask, what is this piece compared to the entire B quadrant? All right, and we know that this piece is 13% of the entire universe. So last question is, what percentage of the entire B is the entire universe? What percentage of the entire universe is the whole of B?
I thought we already decided that's 32%.
The answer we got to was 32%, but tell me the whole B. How big is this whole B?
41.
Yeah, right? And this little part here is 13.
So it'll be roughly less than half of it.
Yes. Be about 32% of it. We would calculate that by dividing this section of AB by all of B. All right, let's move on. The last question was a probability tree. Okay. In blackjack, does anyone play blackjack? Players are initially dealt 2 cards. If the first 2 cards add up to 21, then it is called blackjack. So, in order to hit blackjack, one card must be an ace, which would be a value of 11, and the other card must be 10, jack, queen, or king. So the face cards, jack, queen, king, they are worth 10. Ace is worth 11. You want to get 1, 10, jack, queen, king, and you want the other one to be an ace, for sure. The card order does not matter. Using a regular 52-card deck, please calculate the probability of hitting blackjack. How are we going to approach this, Nikita? Yes, I like a probability tree diagram. Because we could do this one event after the other, like what's the probability of the first draw, the probability of the second draw. But because order doesn't matter, there's going to be so many different moving parts to this. So let's create a tree, and let's say draw 1, first draw 1, and we'll do draw 2. Draw 2. Okay. So, all right, the first draw. All right, we're going to start the node. All right, and we're going to have various branches that come off this node of the possibilities that we care about. What are the possibilities that are relevant to us in this first draw? Ace is one thing that might be useful. Ace. All right, ace. Okay, what's another possibility? Shivu?
10.
A 10? Yes, a 10, and we can lump 10s in with something else that would be very similar to drawing a 10, like a 10 card. What else might we draw that would be the same value as a 10 card? Face card. Face card, right? So if you draw a jack, a queen, a king, there it's worth 10 points. So that's the same as far as we're concerned. We could break them down into each, but it's unnecessary because they're all worth 10 points. So 10, jack, queen, king. Okay. Third possibility is neither. Neither. N-E-I-ther. Okay. So that is 100% of the possibilities that could happen, right? We could draw an ace, we could draw a 10, jack, queen, king, or we could draw neither. There's nothing else that could happen. So we know all these 3 things have to add up to 100%. So let's calculate the probability. What's the probability of drawing an ace? It's going to be the number of aces in the deck divided by the number in the sample space. So how many aces are in the deck? 4 aces in the deck. How many cards in the deck? 52. Excellent. Fantastic. How about 10, jack, queen, king? What's that? 13? Alright, I don't know, but I like the 52. Why do you say 13?
I got each jack, 1 for jack.
How many 10s are in the deck?
4.
How many jacks?
4.
Queens?
4.
Kings?
4. 16.
16. Outstanding. 16. How many total cards? 52. Outstanding. All right, then how about neither? Someone say 0. Did you say 0?
Sorry, 52 by 52. No.
Well, we know that of
30
these...
by 52.
How much?
30 by 52.
Okay. So we know there's 52 total cards in the deck. 4 of them are aces. 16 are 10s, jacks, queens, kings. How many are remaining?
32.
32. Did you say 32, Nikita? You said 30. All right. And the correct answer is 32. Okay. 32. Sorry, didn't mean to remind you were wrong. I just wanted to make sure I heard you correct.
Yeah.
All right. So 32 divided by 52. Okay. I decided to use red for this as I got going. Probability is 4 over 52. Okay. So, the cardinal rule of the probability trees is that the branches in each node sum up to 100%. And this meets our probability. We're good. We're ready to move on to draw 2. See what happens there. Now when we move on to draw 2, we look at each branch separately. First we look at the ace. What are the possibilities that could happen if we draw an ace the first time? The possibilities of relevance to us.
3.
Well, there's what is the card or cards we hope to draw? We drew an ace the first time. What do we hope we draw next time? Sheba, helps out. 10. Do just a 10?
10, Jack, King, or
10, Jack, Queen, King.
Right.
Okay, so if we drew an ace the first time, the second time we're fingers crossed, 10, Jack, Queen, King, 10, Jack, Queen, King, please, 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 right? Then we're going to hit blackjack. So that's one possibility that could happen. We don't care if it's a 10, a Jack, a Queen, or a King, just as long as it's one of those. So, my color's right, yeah? 10, Jack, Queen, King. All right? What else might happen? Hit it an ace, right? Well, what happens if we hit an ace?
We're done.
We're done. We don't hit blackjack. What else falls in the we're done, we don't hit back blackjack category? Everything besides these 4. Right? So, neither. N-E-I-T-H-E-R. I just have to spell out neither. I before E is an exception. Okay, so those cardinal rule of decision trees, the branches coming off of each node must sum to 1. Have we encompassed everything that could possibly happen in the second draw, given that we drew an ace on the first time? Yeah, we have. So all we need to do now, for this part, is to put in the probabilities. All right, what's the probability of drawing a 10, Jack, Queen, King? Probability. How many 10s remain in the deck? 4. How many Jacks?
4.
Queens?
4.
Kings?
4.
Yes. So 16 total winner cards. How many total cards remain in the deck?
51.
51. Right on. All right. We're good there. What are the possibility on the second draw of drawing neither? So there's 16 ways we could win blackjack. How many ways would we not win blackjack? How much?
5.
Yeah, I like 35. So there are 52 cards remaining. 16 are winners. So 51 minus 16 equals 35. Right? So there are 35 chances of losing over a total of 51 cards remaining in the deck. Okay? Let's take a look at this second node. All right, that's the end probability for those first 2 draws if we draw an ace first. Another chance, another way we could win is by drawing a 10, Jack, Queen, King first. Okay, so we draw 10, Jack, Queen, King. We're like, pray to God we hit a what?
Ace.
Ace. Yes. Ace. All right, then we win. Yes, blackjack. What else might happen? Not ace, yeah. I don't know if neither works. work, so I'll just say, because it's only one not ace. Okay? So we either draw an ace or we don't. That's the entirety of what might happen on the second draw. What are the chances of hitting an ace? Like it. 4 aces remain and 51 cards remaining in the deck. All right, how about not ace? How many cards in this remaining deck of 51 are not ace? 47? Does that make sense, Shiva? All right, so we drew a 10, Jack, Queen, King the first time. So right off we know that there are only 51 cards remaining in the deck. The one that is missing is a 10, Jack, Queen, King. So we know that 4 of them are still aces. So 4 out of those 51 we could hit our ace. Alright, so we have this deck of 51. I hand you a deck of 51 cards. There's 4 aces in it. How many are not ace?
Remaining.
The remaining?
Right.
So 4 are ace. How many are not ace?
Right. Remaining.
Tell me the number. How many are not ace?
That's at 47.
47.
Right.
Yep, 47 out of a total of 51. Bingo. Okay, let's look at this third possibility. Suppose on the first draw we draw 7, something not ace, not 10, Jack, Queen, or King. And what do we say once we see that first card? Oh, damn it, lost my money. Well, maybe you didn't lose your money, but you didn't hit blackjack. I think there's a way you could get it. You can add up to 21 later, but you don't hit blackjack. So we don't care what happens on the second draw. We didn't win. So all we need to do now is calculate the end probabilities for each of these scenarios. And since we've made adjustments for first draw, second draw, based on the previous thing that happened, we can multiply straight across for end probabilities. So to find the probability that you draw an ace, and then a 10, Jack, Queen, King, we multiply 4 over 52 times 16 over 51, and we get 4 over 52 times 16 over 51. What do you get, Nikita? 10? There's no 10. I don't see any 10. I just see 4 over 52 and 16 over 51. What? 0.39? I don't like it. You tell me you have a 40% chance of this happening? That sounds a little high. What do you get, Dr. Williams?
0.314.
0.314. I dislike that as well. You tell me you have a 31% chance.
I know you're right.
Why don't we start down here? Should we start with the 32 over 52? What's 32 divided by 52?
0.615.
0.62. All right, so there's a 62% chance that on the first draw, you miss. Sounds pretty reasonable, because there are 32 cards in the deck out of 52, which you would say, darn it, I didn't hit it. 32 out of 52, oh man, didn't make it. So that's a 62% chance that you lose right off the bat. So now let's look at these other possibilities. And given when we add 62 to all these other possibilities, it better add up to 100. Otherwise you did something wrong. So 4 divided by 52 times 16. Let's With a 4.
0.024.
How much?
0.024.
0.024. Alright. 2% chance of that happening? That sounds reasonable to me. So you go 4. How Nikita got that was 4 divided by 52 times 16 divided by 51. You could even in your, I guess in your calculator you could punch in 4 times 16 divided by 52 divided by 51.
4 divided by 52 times 2.
Yes, do it that way. Either way. Okay. Let's do this
0.053.
0.053 is awesome for the second one?
Yeah.
Yep. 0.053. I like it. Now, let's take a look. All right, can we make, oh, no. Right, this is not the reciprocal of this scenario. We can't really make our lives easier and say the math is the same because here we're 16 over 51, here we're 16 over 52. Darn it, 4 over 52, 4 over 51. Yeah. All right, we're going to have to crunch it out. We're going to have to multiply 16 over 52 times 4 over 51 to get the end probability for this. What do you got, Nikita?
0.024.
0.024?
0.024.
Ah, I guess it comes out to the same thing. Right? Works for me. 16 over 52 times 4 over 51 comes out to 0.024. And how about this scenario? 16 over 52 divided by 47 over 51. 0.28. Okay. 0.28. Okay. Now, what do you get when you add up all 4 of those, or all 1, 2, 3, 4, 5 possible roots to the end of this hand? One. Yes. Dr. Williams?
Made a mistake.
Shiva? One point. All right. Close enough to 1 for your comfort, Dr. Williams? All right. So all of these together add up to 1. There are 1, 2, 3, 4, 5 paths to the end of this hand. How many paths include blackjack? Does this include blackjack?
Yes.
Yes, blackjack. Bingo. How about here? No. How about here? Yes, blackjack. How about here? Nope. How about here? Nope. Okay, so there are 2 ways we can get blackjack. And so we add those 2 together. 2.4% plus 2.4% gives us 4.8%. So 0.048, 0.024 plus 0.024, or 4.8% chance of hitting blackjack. So every time you hear someone in a casino yell out, "Blackjack!" Hey, what were the chances of that happening? 4.8%. Make sense? Okay. ready to move on? Let's turn our attention now to tonight's material, which is going to be a continuation of this probability. First thing we're going to talk about is random variables. So let's turn our textbooks to page 466. I'm going to talk a little bit about random variables. Page 466, there's a graph I want to point out to you. In this example on page 466, the National Health and Nutrition Examination Study asked people how many hours of TV you watch each day. And people who answered this question answered. And then about a third the way down, we get the probability for each answer. Let me go ahead and make some room here and jot this down so we can discuss it as a class. So, x, probability of x. Right. X, probability of x. Alright, the folks who did the survey said, how much TV do you watch? And the answers they got were between 0 and 6 hours. So 0, 1, 2, 3, 4, 5, 6. Alright? 13% of people said, I watch 0 hours. 24% said I watch 1 hour. 24.33, 0.14, 0.07, 0.07, 0.02. Right, so this is the data. 13% of the people said I watch 0 hours of TV. How many people said I watch 3 hours of TV? Jiva?
14.
Excellent. How many people said I watch 5 hours of TV, Nikita?
7.
7%. All right. So X, in this scenario, takes on the quality that we call a random variable. It is random because we don't know what it's going to be. We don't know what you're going to say when we ask you how many hours of television you watch. Could be 0, could be anywhere up to 6. So if we were to plot all of this data, let's see, let me do this quickly. So we've got, if we were to plot this on we're going to call this percentage of people on this graph, this vertical graph, or call this number of TV hours, number of hours. On the horizontal, number of hours. All right, we would have 0 through 6 as our possibilities. Let me see, we've got as low as 2% and as high as 33%. So let's call this, break this up like 10%, 20%, all this 30%. So, well, 0, use a different color here. 0, 1, 2, 3, 5, 6, 7. All right, so let's see. 0, we've got about 13. 1, we've got about 24. 2, we've got about 33. 3, we've got about 14. It's going to be about here. we've got about 7. 5, we've got about 7. 6, we've got 2. We don't need this last spot. So if I were to draw this in a frequency distribution, I could look at it in such a fashion as this. And I could tell you, all right, this is the way the data looks. And of all the people who watch TV, suppose we're making some sort of assumption about the rest of the population. We'll talk a little bit about how this relates to statistics next week. But this is the frequency distribution of this random variable. Now, if I were to ask you, what is the average amount of TV that a person watches based on this data? How might you go about answering that question? Now we look at their frequency distribution, and we've got 2 hours is the biggest hump, right? At 33%. So would you say the average is 2 hours? Yeah, all right. So, but what about all this stuff on the right side? The people who watch 3, 4, 5, 6. How do we account for that, Sheba? What about all the people below? How do we account for that? Well, the answer to that question is we take a weighted average of all the data. What that means is we take 0 times 13%, and we add it to 1 times 24%, and we add it to 2 times 33%, plus 3 times da-da-da-da-da-da-da-da. We add them all together based on the percentage likelihood of that answer. So any person we ask, the chances of them saying 1 hour of TV is 24%. Any person we ask, the chances of them saying 5 hours of TV is 7%. So to account, Shiva, for all this stuff on the right side and all the stuff below, the highest, most common point, we're going to take that weighted average. So here's what we're going to do. I'm going to write it out. At the same time, though, you can start punching it into your calculators. So 0 times 0.13 plus 1 times 0.24 plus 2 times 0.33 plus 3 times 0.14 plus 4 times 0.07 plus 5 times 0.07 plus 6 times 0.02. 2.07. All right, let's see if the rest of your classmates arrive at that same answer. Answer. Keep your fingers crossed, Nikita. Please. We got it right. Blackjack. 2.07, Dr. Williams? 2.07. That is the average TV that Americans watch based on this data. And what brings us now, we can extend this term average, as we know it, to a term that we will use in statistics and finance and lots of quant courses, to this term of expected value. This equals the average. It also equals the expected value. this case, it's just an average of how much TV people watch. But it could also be the amount of money you expect to win. It could also be the amount of, batters you expect to strike out. It could also mean the amount of volatility you expect in this derivatives trading. We take all the possibilities that could happen, and we take the percent of each of those possibilities happening, and then we do a weighted average, and we could call that weighted average, and we would be right. But now we just learned a fancy new term, expected value. Let me give you a simpler question. Suppose I were to do this same survey, and I came up with slightly different numbers. Suppose I had 1, all right, 0.5. Okay, suppose I did this survey again, and 50% of the people told me they watch 1 hour of television, and 50% of the people told me they watch 5 hours of television. All right, so it sounds a little weird, fine, but let's just suppose that happened. What would be the expected value, the average amount of television watched by an American? 3 hours. Does that make sense? We can just look at it and say, well, half the people watch 1, half the people watch 5. All right, halfway between 1 and 5 is 3. Or we could also calculate the math and say 1 times 0.5 plus 5 times 0.5 equals 3. And that gives us expected value. Any questions? You got it, Shiva? All right, let's try a couple examples from your textbook. Let's go to 9.1, page 471, and let's look at number 10. 471, number 10. You're given a similar random variable probability distribution, and you are asked to find the expected value for each random variable. Number 10. Go for it. All right, Sheba, what do you got?
I did it wrong. I got 15.5.
All right, well, you're in the right neighborhood, but yes, it looks like there's maybe one key you pressed incorrectly. Dr. Williams?
4.
4, and looks like maybe 2 keys you pressed incorrectly. Nikita? 25 is the correct answer. So we need to take 0 times 0.15 plus 15 times 0.2 plus 30 times 0.4 plus 40 times 0.25. And on that finance calculator, you just need to get your system. And it's easy to make this. Number 10.
Oh, 10, okay, I was doing 9.
Oh, I said, well, let's take a look at number 9. You got 4?
10 is 25, yes.
You got 4 for number 9?
Yeah.
Yes, that is the correct answer for number 9. So we're good. All right, Sheba, you understand the theory,
Yes.
right?
Yes.
Fantastic.
Got it.
All right, let's move on. Let's take a look at number 17 and start talking about some real money. Couldn't read that. Think about how you would solve that. Let Let me make some space. We'll work this one together because there's a new nuance that we need to go over, but I want you to go ahead and start thinking about how you might solve this one. Righty. In one form of roulette, you bet $1 on even. If one of 18 positive numbers come up, you get your dollar back, plus another dollar. If one of the other 20 numbers come up, you lose $1. You lose your dollar. All right, your task now is to find the expected value. So, we've got two things that could happen. Your even could come up, and you win $1, plus you get your dollar back. And non-even number could come up, and you lose your dollar. So we need both components of each of them. One, the probability of that happening, and two, how much you win or lose. So let's take a look. So let's look at win, and let's look at lose. All right. What is the probability of winning? Probability of winning.
18 over 38.
18 over 38. I like it. What's the probability of losing?
20 over 38.
20 over 38. All right, so this is already looking not so good, right? Hopefully they give you free drinks. You enjoy the atmosphere? All right, how much do you get if you win? And you need to think about this, like how much money comes into your pocket, and if you lose, how much money goes out of your pocket. Don't get confused of like, well, I put $1 on the table, how does that work? So if you win, how much more has your wealth increased?
100%.
But dollar terms. $1. Exactly. All right, so you win, your net worth is increased by $1. What if you lose? How much, Nikita? $1, yes. All right. So your net worth has decreased by $1. Okay, so let's do our weighted average magic. Switch markers. And let's do 18 over 38 times $1. And let's add that to 20 over 38 times negative $1. Let's see what we get. 18 over 38 times 1 plus 20 over 38 times negative 1.
Minus 0.053.
Is that what you get, Dr. Williams?
The nickel, yes.
Yes. What do you get, Shiva?
I didn't get that.
What did you get? All right. You really need to like get fluent with that. Is that a new calculator, by the way?
Yeah.
Oh, that looks great. So just really spend some time getting fluent with that.
Okay.
So you don't want this stuff to be slowing you down. So if you were to punch in 18 divided by 38 times 1 plus 20 divided by 38 times negative 1, you would get negative and this negative is ever so important. Negative 5.3 cents. So what does that mean? Every time you sit down at the roulette table and bet even, right? What is your expected value? Every time you sit and take this bet, how much money are you expected to win or lose? 5 cents. So it's basically going to cost you 5 cents every time you want to play.
Well, it costs you more than that. I mean, if you lose the dollar,
Yeah.
it costs you $1.05.
It costs you $1 each time you lose, but you don't lose every time, right?
Well, that's true. The odds are right. Yeah.
Sometimes you win. Okay, so sometimes you lose $1, sometimes you win $1, but over time, your expected value, the expected amount you mathematically might lose, is 5 cents. Now, it doesn't make sense because you're not going to lose 5 cents on any one occasion, but that's how much money you are expected to lose each and every time. So suppose you were to do this 100 times. You're to play 100 times. How much money do you think you would lose or win? So you play 100 times. $100 times. Play 100 times. Tell me how much money you're going to win or lose.
$5.30.
You're going to win? You're going to win $5? What's that?
Win.
You're going to win. You're going to come up with an additional. All right,
No, I mean, I didn't do the minus.
$5.30. Positive, or you're going to win or lose?
You're going to lose.
Yeah, yeah, you're going to lose. All right. So if you do this 100 times, your odds are you're going to lose. We'll say $5.30, or we might say $5 or $6. Because you can't lose $5.30, you can only lose 5 or 6. Those would be your odds. So playing this 100 times, you probably would have contributed $5.30 to the casino.
And actually, I think that's their rate they take, isn't it?
No, they don't take a percentage. They give you odds that favor them, though.
I thought I saw somewhere in our reading that basically their cut is about that. I may have missed it.
Well, I know when you play poker, sometimes they'll take a percentage of your winnings. Maybe it's about that. But they're not taking anything beyond this. If you win, they'll give you your $1. If you lose, they'll be happy to take your $1.
Well, I guess the one I was making on the odds, they expect you to lose this. And so that's really kind of how they make money.
Yeah, they expect you to lose 5 cents every time you bet $1. So maybe they want you to bet more than $1.
Lose more.
You bet $100, they expect you to lose $5. So you do this 100 times, and you bet $100 each time. You're going to lose $500 or $600. Could be your average, and then maybe you say, "Well, I lost $500 or $600. Now I want to start betting 1,000." Yes.
It says if if one of the 18 positive even number comes up, you get $1 back plus another one. So we get $2.
Yeah, so that's what I mentioned before. How much after you just play this one time and you win? How much more money do you have in your pocket? Your net worth is increased by 1. So you play this one time and you lose. How much less money do you have in your pocket? Your net worth is decreased by 1. It gets a little confusing because you're like, the dollar on the table, does that count as 2? You just think like, what did my net worth increase by? What did my net worth decrease by? And then the odds of that happening, weighted average gives you expected value. Okay, what else did I have here? 17. How about 19? Let's take a look at number 19, and then we'll take a little break. Number 19, go ahead and work that out to the best of your ability. Critical. You think Casino's going to give you a 50-cent chance? An expected value of 50 cents every time you play numbers?
No, it should be negative.
Bingo. 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 Alright, so Shiva, just think of it the same way. What's the probability of winning? How much do you win? What's the probability of losing? How much do you lose? Do the weighted average. All right, let's do this. Do you need another minute, Nikita? All right, take it. What's that?
0.
All right, let's do it together. Okay, what's the probability of winning?
1 out of 1,000.
All right, so you pick one number. There are 1,000 possible numbers between 0, 0, 0, 0, and 999. All right, so 1 through 999 plus the 0, 0, 0. So there are 1,000 possible things that could happen, and only one way for you to win. Probability of winning is 1 in 1,000. Doesn't sound as exciting once you look at it like that, right? Maybe that's why I said the 999. All right, how much do you win if you win? Plus. And how much does your net worth increase by?
499.
Yes. 499. All right, because you're just getting your dollar back. They're not getting an extra dollar. All right, what's the probability of losing? There are 1,000 things that could happen. How many of them entail you losing?
1 by 1,000. And then using $1.
999.
Yeah, there's 1,000 different numbers. If one of them comes up, you win. If the other 990 come up, you lose.
999.
Yeah, did I say 999?
Said 999.
990? 999. Don't forget those extra 9 ways that you could lose. Alright, so that is the probability of losing. How much do you lose if you lose?
1.
$1. Yes, negative $1. Your net worth decreases by $1. So let's crunch that out. Let's go 1 over 1,000 times 499 plus 999 over 1,000 times negative $1. All right, and what do we get when we do that math?
50 cents.
Close. In theory,
Negative 50 cents.
negative 50 cents. Negative 0.50. Ever so close. So, on average, it's going to cost you 50 cents to play this game. You're going to have to play it quite a few times, though, before you win even once. Before you're likely to win even once. Is that feeling good in terms of expected value? You feel like you have a good grip? Your expected value every time you play this game is negative 50 cents. Your expected value every time you bet $1 on this roulette, even on roulette, is negative 5 cents. Now you're going to win $1, lose $1. In this case, you're going to lose $1, win 500, or win 499. Excuse me. But over time, this experiment repeated over and over again. We need to be conscious of what statisticians, financiers, risk analysts call expected value. And we can learn to calculate that. Great, so let's take 10. You don't need more than 10, do you? We just have two fairly simple concepts. I mean, they're not simple, but they're friendly in terms of not a lot of calculations, just some intuition. So let's come back at 8:18. I'm going to recharge this battery here.